In this lecture, I focus on changes observed in the ocean and the cryosphere. Okay, it's the continuation of the previous lecture, which looked at changes in the atmosphere, the hydrological cycle, and ecosystems. So this lecture has two parts. In the first part, we focus on the ocean. We look at changes of the heat content, the sea level, and the pH and associated with changes in the CO2 concentration. Okay, well, I'm talking about ocean acidification. Here's the link. In the second part, we focus on the cryosphere, the ice system. We look at changes of Antarctic and Arctic ice coverage. And we look at changes in the Greenland ice sheet. We look at permafrost changes and changes of glaciers. So let's start with the ocean. Okay, let's focus on the ocean. And the first thing we look at is the heat content and heat content changes. So we want to know, how has the heat content of the ocean changed? The way to do that is you can separate the ocean into little boxes, like shown here in this little sketch. And for each box you can work out the heat content. The heat content is the volume times the density times the specific heat times the temperature. And you can do that. You need a measurement of temperature, and you need to look up values for the specific heat, and so on. You can do that. Okay? And if you have a temperature profile from the surface to some depth, you can work out what is the heat column, the heat content of your water column from top to bottom. And this is in terms of an integral. You can write down an integral, which means the sum of all these little boxes. Okay? And then you can also do it horizontally, because if you have measurements of temperature throughout the world ocean, okay, we can work out the entire heat content of the oceans. And this is done with Argo floats. Argo floats are instruments that measure temperature and salinity and start at the surface. They sink to a certain depth. In the past, it was down to 700 meters, but nowadays they go to 2,000 meters and even more. And they record the temperature, and then they hang around a little bit at depth, and they rise back to the surface, and they transmit data to satellites. And the map above my head shows you the global distribution. We have many of these Argo floats, several thousand of these Argo floats in the ocean, continuously measuring these profiles. So that's what we use. And then we can work out the heat content, but more importantly, we can construct a time series. How has it changed? Okay. And this is what's shown here. Heat content changes in the upper ocean. Okay. So what's shown here are time series of the heat content relative to a start point, which is around 1950. So what's shown here are changes relative to the heat content of 1950. Okay. And the initial reconstruction is not based on Argo float, it's based on ship-based measurements, and the accuracy is relatively low, but it becomes better as you move on later into this time series. And you can see that the heat content increases. We get an increase. There are some variations in there, but overall you can see that the ocean is heating up. And the ocean is heating up at a higher rate compared to the land and the atmosphere, which is also included in this graph. Again, that's what we learned from these observations. We can work out how much heat ends up in the ocean, how this has changed. And we can even work out an equivalent heat flux, surface heat flux anomaly that actually is the cause of this ocean heating. Okay, and so we can look at the entire heat balance of the climate system, and we can work out that the warming of the upper oceans actually accounts for about 63% of the total increase in the amount of stored heat in the climate system. From 1971 to 2010, so this is this particular study, and warming from 700 meters to the ocean floor, it's about another 30%. So altogether, the oceans receive more than 93% of the total heat increase of the climate system. Okay, you learned about the greenhouse effect. You learned about greenhouse gases introduced by humans into the climate system. And here you learn that the majority of that energy actually ends up in the ocean. Okay, much more than compared with the soil, okay, with the land or the ice. Okay. In this graph, there's also a little bit more information. It's about the uncertainty of these estimates, which initially is very big because we didn't have that many measurements in the ocean, and the uncertainty becomes significantly less as we move into the future. Okay, because of Argo floats. And if you read something like 700 meters, this is just because the initial Argo floats were limited to 700 meter depth, and nowadays they go much deeper. Okay. This is about the heat content. So there's another thing happening if you warm up the oceans, and this is what we call thermal expansion. Okay, if you heat up seawater, it expands. Okay, and because the oceans can't expand much horizontally because of the continents and the coasts, a little bit but not much, the major expansion is vertical. Okay, so this is the link to sea level rise. This is the second point here, the sea level rise. So what causes the sea level to change? So one big component is thermal expansion. Okay. The second important point comes from the addition of ice from the land melting in the ocean. Okay. So we're talking about the exchange of the water stored on land by glaciers and ice sheets and the melting of that. These are the two major contributions. There's other additional effects, which to do with terrestrial water storage and groundwater exchange and changes of the hydrological cycle, but they are not that important. Okay. So now the sea level change can be derived from tide gauge data, okay, and satellites. And you also have to account for something that we call the post-glacial rebound, okay, because the continents on average are rising relative to the sea level, as part of an adjustment process. Anyway, so let's have a look at reconstruction of sea level rise and the attribution of different causes. And this is from a study published by Katja Dominguez. And Katja was a PhD student at Flinders University. Okay? So let's have a look at the sea level rise reconstructed. So we focus on the upper graph. There are several curves in here which shows you contribution to sea level rise. Okay, and the reference is 0, and then we go up to 20 millimeters as a time series from 1960 to 2010, around that time. Okay? And then you can see sea level rise due to thermal expansion is the red curve. This is from 0 to 700 meters. Okay, and it's because these Argo floats didn't go deeper. This is why we have only measurements to 700 meters, and the deeper parts have been estimated. The deep thermospheric sea level is it's called here. So this is the thermal expansion of waters deeper than 700 meters. Okay, and you can see these estimates. Here you can see contributions from the melting of Antarctic and Greenland ice sheets. It's a blue curve as an estimate here. And the contribution from glaciers and small ice caps. Okay, and some estimates of changes in terrestrial storage. Okay. So now if you add up all these components, add them all up, you come to the blue curve in the lower graph. This is the sum of all these contributions, and you can compare it with observations derived from tide gauges. Okay, there are two curves in here based on tide gauge, and you also have estimates from satellites, satellite altimeter measurements. Here is the red curve, the red dashed curve. So you can see that this reconstruction works out well. Okay, what we learn from that exercise is that while both thermal expansion and the melting of sea ice equally contribute to the observed sea level changes. Okay. So the reconstruction agrees with tide gauge and satellite observation. So overall, we're only talking about something around 6 centimeter change here over that time scale. But the more important question is, well, how much do we get by the end of the century? Do we get 2 meters or maybe more? Because that is a fundamental question of significance to coastal communities if we're looking at that order of sea level change. Okay, and this is the estimate based on observations that we have. Okay, trend corrected. Okay, for post-glacial rebound, and we're talking about 3.42 millimeters per year. And it indicates that there is an acceleration since 2010. You can see that the curve gets a little bit steeper towards the end. Okay, so this is the story about sea level rise and the link to the global warming that we are experiencing. Let's talk about ocean acidification. Okay. Ocean acidification is linked to changes of CO2 in the ocean, okay, or an uptake of CO2 by the ocean. But let's start with the CO2 story first. What's shown here is, on the left side, the distribution of CO2 before the industrial revolution started. Okay? It's a reconstruction of distributions in the ocean. And we're looking at the Atlantic Ocean, the Indian Ocean, and the Pacific Ocean. And we're cutting through all these oceans, and you can see the distributions. Blue is low, yellow, orange, and red are high concentrations. And I discussed the reasons for these distributions in the previous lectures. What we're doing now is we look at the changes due to human emissions of CO2, okay, into the atmosphere and ending up in the ocean. And we can see these increases by the red and yellow regions here. These are the areas that have experienced the largest increase in CO2 in the ocean. And if you look at the details, you actually work out that the ocean has absorbed around 25% of the anthropogenic CO2. 1/4 of the CO2 has ended up in the ocean. So without the oceans, the effect would be much bigger in the atmosphere. Okay, the greenhouse effect would be much bigger. But the oceans have taken up CO2. Okay. So most of the CO2 has been taken up within the upper half to 1 kilometer of the water column. Okay. And most of the CO2 is concentrated in subtropical gyres. Subtropical gyres here, if you cut through the oceans, are these areas here. It looks like a bowl shape on both sides of the equator. You can see that here in the Pacific Ocean as well. Okay? Little anthropogenic CO2 has appeared in the deep ocean. And that's because of the time scales. Okay, we're talking about changes here on time scales of more intensified in the last 10, 20 years. Okay, and it's obvious that because of air-sea gas transfer, that it ends up in the upper layers of the ocean. Okay, and this is what actually causes, or it's a link to the ocean acidification. Because of that CO2 increase in the upper layers of the ocean, there is actually a chain reaction happening, a change in the carbonate system of the ocean. And we have a look at that now. Okay, it's shown here in this diagram what happens, okay, with CO2 in the ocean. Okay, so you have that flux of CO2 into the ocean, and in CO2, what it does, it reacts with seawater and forms carbonic acid. Okay, the carbonic acid becomes converted into hydrogen ions and bicarbonate ions that further, okay, split up into carbonate ions and hydrogen ions, and even more hydrogen ions. So that's the end product we're talking about: hydrogen ions, carbonate ions. So what's so significant about that? The hydrogen ions is something that we measure as pH. Okay? We measure the hydrogen ion concentration as the negative logarithm. Okay? And this is what we call pH. Okay? So we can measure the changes of the concentration of hydrogen ions as changes in the pH value. Okay. The carbonate ions, that's the link to the important bit here, is needed for the production of calcareous plankton, like coccolithophores, which are shown here. Okay. For the production of these special plankton species, you need particular minerals, carbonate minerals, which are calcite and aragonite. These are essential. Okay? So now, at this current time, we have enough of these minerals in the ocean down to a certain depth. And this is what we call the saturation horizon. Okay, above the saturation horizon, we have enough of these minerals, and below, we don't. Okay, now it's all about how does a change of CO2 in the ocean change this saturation horizon. Okay, if it moves upward, even to the surface, means that the waters become undersaturated in critical carbonate minerals. Okay, and so that these species up here can no longer form. instead of a formation, there will be corrosion. There will be corrosive environments, and these will imply dramatic shifts in marine ecosystems. Okay? So now comes the key part in this little sentence here. An increase in CO2 in the water, in the seawater, leads to an increase in hydrogen ions, which means that the pH value drops, but a decrease in carbonate ions. And this decrease is the critical bit, because this implies that your saturation horizon will move up in the water column. So let's have a look at the projections, because we can now predict what happens in the future. These are predictable reactions in water, and if we make assumptions of how the pH will decrease in the future, we can work out how the concentrations of carbonate ions will change, will decrease, and how the saturation horizon will change. And this is shown not in this graph, but this is one step before we do that. So what this graph shows you is the link between atmospheric CO2, the CO2 in the ocean, and the pH. Okay, so the red curve is the Keeling curve, atmospheric CO2 concentrations, the increase since the mid-1950s, okay, shown here until 2010. On the left axis is the CO2 concentration in the atmosphere in units of parts per million, okay. And then you can see other curves. This one is the CO2 concentration in the ocean. And you can see there are huge variations here, but you can see a similar trend. And this is because if you increase the CO2 concentration in the atmosphere, through the air-sea gas exchange, the concentration in the ocean increases. Because of that, we have now these chain reaction that happens in the ocean, an adjustment of the pH to this change, and the pH drops. Okay. So far, ocean pH has dropped from 8.2 to 8.1 since the Industrial Revolution, corresponding to a 25% increase in hydrogen ions. Okay, that's the storyline. And now we can look at what happens in the future with these critical carbonate minerals. Looks like a busy graph here, but let's have a look first at what's shown here at the bottom. Okay, you can see atmospheric CO2 concentrations go up. Okay, and you can see that the surface ocean pH goes down. Okay. So this now converts to changes in the surface saturation of calcite and aragonite concentrations. Okay, they will drop. Blue is calcite, green is aragonite, and it will drop because the saturation horizon will move upward. Okay. So, and this is now shown here on a scale where the level 1 means this is the threshold. If you drop below 1, you'll have undersaturated conditions. This is the critical case. And in this example, it doesn't happen. The aragonite levels drop, and the calcite levels drop, but there's still a sufficient amount in the water. But that's not the case for different regions in the world ocean. Let's look at the Arctic Ocean. Okay? You can see that the green curves are lower in all cases, so aragonite is the critical component. And you can see that there will be undersaturation predicted before the end of this century. The Southern Ocean, same feature. Undersaturation in aragonite predicted before the end of the century. And this is what we're talking about when we're talking about ocean acidification. It's not the fact that the pH levels drop. It's not the fact that the levels of calcite and aragonite drop. The critical thing here is that it's reaching that level of undersaturation, and that flips around the way the ocean works in terms of these calcareous plankton and associated marine food webs. All right, so this is the story about ocean acidification, and that's the end of the first part of this lecture.